Crosspol jamming is a possible countermeasure against terminal phase radar homing missiles. Now, the overall purpose of this video is to begin to clear up some misconceptions about crosspol jamming that, in the past, seem to have obstructed its use as an easily deployed and highly effective countermeasure.
A good place to start is why listen to me? Why do I have anything to say? Well, after 37 years in active onboard angle deception countermeasures and working in real-time ECM effectiveness assessment, I've learned some things that I can share with you. I've spent a lot of time in hardware-in-the-loop trials, both anechoic chamber and air carry, with real seekers. What's the count? I don't know. 9 different types of seekers and 16 examples with their autopilots in some cases. I've spent more than 20 years developing a simulation application to represent an engagement between a missile and a ship and all aspects of that, particularly angle deception countermeasures, including crosspol, and cross-eye and various versions of cross-eye. And most importantly, I've spent a lot of time comparing the simulation output with the hardware trials results to validate the simulation. And so that's really where the gold is. So I want to share with you some of the things that I've learned.
Okay, crosspolarization jamming or crosspol jamming is an active onboard angle deception electronic countermeasure against terminal phase radar homing missiles. Its purpose is to cause guidance errors that make the missile fly a path that misses its intended target. And it can be used to protect surface ships against anti-ship missiles or aircraft against anti-air missiles. Crosspol attacks the seeker antenna, basically the eyeball of the missile, so that the missile's guidance information is damaged before the sophisticated signal processing in the seeker and the autopilot even get started. So it's right at the very front end of the processing chain. Fundamentally, crosspol jamming exploits the fact that the copolar and crosspolar patterns of the seeker monopulse antenna have different shapes, but it doesn't have to be a monopulse antenna. Now, whereas the copolar sum pattern has a single flashlight beam on bore sight, like a single beam on bore sight, like a flashlight has, the crosspolar pattern has 4 beams, none of which are on bore sight. To understand how crosspol works, we need a few common definitions. We need a language of common definitions. So let's start by defining the main parts of a radar homing missile so we can see a bit how it works. Loosely speaking, a missile comprises 5 sections. First is the seeker, right at the nose, the very front, which provides information about the target, including but not limited to angle and range. Now, the seeker has an antenna that is designed to have a radiation pattern, which, as I said, looks like a flashlight. It's got a single main beam that the seeker uses to find targets with and to point at the intended target. The seeker transmits radar pulses, and when the flashlight beam is pointed right at the target, the strongest radar pulses illuminate the target, and the signals reflected by the target go back into the antenna through this highest gain part. Next is the autopilot. The autopilot uses information from the seeker to calculate the guidance signals to fly the missile to hit the target. Next is the flight dynamics section, which uses the guidance signals to control the fins to fly the missile on an intercept path. Then up at the back, there's the propulsion section, like a rocket motor that makes the missile fly. And finally, of course, there's a warhead. Next definition, polarization. And I mean polarization of an electromagnetic wave. This is the plane in which the tip of the wave's electric field vector vibrates. For linear polarizations, this is commonly the vertical plane or the horizontal plane. Alternatively, the polarization can be circular, so the E-field vector's tip traces a circle, either clockwise or counterclockwise, and this is referred to as left-hand circular or right-hand circular. Next definition, the Poincaré sphere. The Poincaré sphere is a useful concept for relating copolarization to crosspolarization. Every point on the sphere corresponds to unique polarization. And so if we're going to use crosspol, we need to know what crosspol is, what polarization corresponds to crosspol for a particular seeker. And that's why the Poincaré sphere is important. Polarizations which are orthogonal to each other or cross-polarized to each other are connected by a line passing through the sphere's center. Left-hand circular polarizations are at the poles, at one pole, right-hand circular is at the opposite pole, and slant linear polarizations lie along the equator. Is the equator stretched out? Opposite polarizations differ by 90 degrees. And left and right-hand circular or elliptical polarizations lie in opposite hemispheres. Next definition, soft kill. Now, when a missile has an unrecoverable heading error, in other words, it can't turn hard enough to hit the target, that's called soft kill. And we want to make that happen with, for example, crosspol jamming. Next definition, hard kill. Hard kill means the missile has been physically destroyed. Quite often this means shooting the missile down with bullets or another missile, but if the missile guidance signal can be fooled into making the missile hit the sea surface, that's hard kill, the same as bullets and anti-missile missiles. Now, the last bit of background information is that the seeker antenna is designed to receive a specific electromagnetic polarization, for example, vertical or horizontal polarization. So let's talk about crosspol jamming. Crosspol jamming means the jammer radiates a signal whose antenna is polarized opposite to the seeker's polarization. The jammer has to make the seeker process this cross-polar signal instead of the expected copolar signal from the target. And remember, the Poincaré sphere defines the copole and crosspol pairs. Crosspol jamming causes the seeker antenna to move, which creates signals that are fed to the autopilot, which affect the flight dynamics, which causes the missile to miss the target in the end. If the seeker is vertically polarized, then the jammer uses mostly horizontal polarization and vice versa. If the seeker is right-hand circularly polarized, then the jammer uses mostly left-hand circular polarization and vice versa. Now, so how does it work, though? Well, crosspol jamming effectively changes the shape of the seeker antenna pattern without the seeker knowing. How the jammer polarization changes the seeker antenna pattern is shown in this video clip. 0 degrees is perfect crosspol, that's vertical polarization. That's when you see the distortion. Loosely speaking, the effect is to split the intended single flashlight beam into 4 beams, so there is 1 beam in each quadrant. Now, in order for the seeker to track the target, it has to point one of those 4 beams at the target, and again, loosely speaking, that moves the antenna pointing direction away from the target. And when the jammer polarization is controlled correctly, the seeker antenna continues to move. Now, at this point in the story, we need to consider a complication. The exact cross-polarization of a seeker antenna can be uncertain. For example, in the case of linear polarization due to missile body roll angle and other factors. So to accommodate this, the jammer polarization, the polarization of a crosspol jammer, is generally varied near the expected angle for perfect crosspol. The progression of the jammer polarization angle versus time is referred to as a crosspol waveform. Now, for linearly polarized seekers, varying the jammer polarization is easy and inexpensive. It is sufficient for the jammer to use a linearly polarized horn, and then a motor and a gear assembly can be used to mechanically vary the horn rotation angle near the expected angle for perfect crosspol for the seeker. The waveform that's shown here is triangular in time. Other waveforms are possible, but that's for another video. So here's an interesting question. Where does the cross-polar response of an antenna actually come from? This is easy to understand and the explanation is intuitive. There are no scary, incomprehensible black magic pieces involved, contrary to popular opinion or belief. So to understand this, let's pick a reflector type antenna as an example, just to illustrate the principles. And that's a paraboloidal reflector fed by a small antenna called a feed, positioned at the reflector focus. Now in this example, suppose the feed is as a vertically oriented dipole. Okay, the polarization of a dipole looks like this. Imagine a bunch of arrows impressed on a sphere and they point from the bottom of the sphere to the top. Now imagine the orientation of the dipole's electric field vector at each point on the reflector surface when the dipole is sitting at the focus, reflector focus. It looks like this. All the vectors are mostly vertical on the reflector surface, but they point outward at the bottom in the bottom 2 quadrants and a little bit inward at the top 2 quadrants. This means that even though the feed is vertically polarized, the reflector is scooping up fields that have small horizontally polarized components in each quadrant on the reflector. These components are cross-polarized with respect to the dipole feed. Now, how much cross-polarization there is depends on how deep the reflector is. As the ratio of the focal length to the diameter gets smaller, in other words, the reflector gets deeper, the cross-polar gain of the overall antenna goes up. In this clip, the right side panel shows a diagonal cut of the Seeker cross-polar antenna pattern, and the left side shows a view of the reflector antenna shape. As the focal length becomes smaller, the reflector becomes deeper, and the cross-polar gain goes up as expected. Now let's put the brakes on for a second, try to understand one of the many aspects of cross-pole jamming that, as far as I can tell, everybody else misses. Now very often, a paraboloidal reflector isn't fed by a dipole, it's fed by a waveguide, which looks, for example, like this. Here's the feed from an MG13 fire control radar. Basically, the feed is a splash plate over 4 half-height waveguides with flanges around them to make it behave a bit like rear-facing horn antennas, facing towards the reflector. And here's the feed of an APG 502 fire control radar. It's the same sort of idea, half-height waveguides. So here's a question. What happens when you try to excite a waveguide with the opposite polarization as it's designed for? The answer? The guide is in cutoff. That means there is literally no transmission at all within the guide. The E-field amplitude decays exponentially by the wave, according to the wavelength, starting at the waveguide entrance, right at the throat of the guide. A Seeker antenna with a waveguide feed does not receive cross-polarized signals, full stop. A guide which is oriented for vertical polarization direction will propagate no horizontally polarized signals whatsoever. Absolutely no cross-polarized signal will propagate down the guide. That said, how does crosspol work? Well, consider the E field on the reflector when it's illuminated by a crosspol jammer. All we have to do is rotate the field on the reflector by 90 degrees from what we showed before for the feed, like this. Aha! What were small horizontal vector components before from the feed have now become small vertical components. What was a cross-polar E field on the reflector before has become a copolar E field as seen by the feed, and that will propagate in the waveguide feed. And how interesting is this? Notice that the sign of the copolar component flips from quadrant to quadrant, and that it's 0 in the principal planes. This is why the cross-polar antenna pattern has 4 lobes instead of 1 main beam. The 4 lobes are called Condon lobes. Remember, the radiation pattern of antenna is the Fourier transform of the electric field vector across its aperture. So Fourier transform of this is going to look like 4 beams. And it's simple to show that the sign of the E field lobes in the pattern change from quadrant to quadrant. This is important later when we want to choose the crosspol waveform to fly, for example, a sea skimmer left or right, or an ASL guided missile left or right and up and down. Like choose where we want it to go. Now, to anyone who says this is impossible, I certainly would be interested to see your evidence that shows it's impossible and the path by which that evidence was assembled such that it skipped over the discovery that it is possible. Although you're going to need a couple of other pieces of technology, such as a pointing error estimator and a multipath estimator, but both of those are also possible. There's another crosspol player here. It's the radome. The radome protects the antenna, so every missile has to have one. And radomes are generally made of ceramic or plastic resin and might have multiple layers, including a rain erosion coating, and they are designed to be as radar transparent as possible at the seeker center frequency. The radome causes polarization bending in the same directions as the reflector, so the radome contributes to the cross-polar response of the underlying antenna. This basically falls out of basic electromagnetics and physics. The polarization bending happens because the dielectric constant of the radome material is different from that of air, and because of the double curvature of the radome.
Now, the dielectric constant is important because it determines the wavelength of the electromagnetic wave in the dielectric material. And the higher the dielectric constant, the more the wave is compressed. So when the wave goes from air to the dielectric material, the wavelength gets shorter.
Ultimately, this means that the doubly curved surface of the radome bends the incoming and outgoing polarization. Now, viewed face on and keeping with the vertical polarization example, the polarization vectors again tip out a bit at the bottom and in a bit at the top. Fun fact, the higher the dielectric constant of the radome material, the more polarization bending happens. And the stronger the material is, generally speaking, the higher the dielectric constant. So strong materials mean more polarization bending, and the pointier the radome, the more polarization bending there is. So the radome is important. It means that whatever the cross-polar response is of the underlying antenna, the radome enhances it. Now, how much does the radome affect the susceptibility of the seeker, the missile, to cross-pole jamming depends on several factors, including the shape of the radome, the material it's made of, if it's got multiple layers, and if it does have multiple layers, the properties of those layers, including and especially the thickness of each layer. And broadly speaking, polarization bending is increased by, again, the things that make the radome pointy and a higher dielectric constant in the radome material. Also, the radome is, its electrical properties are a function of frequency because the radome thickness profile is fixed. And this includes the radome's contributions to the antenna's crosspole pattern. So that will also be a function of frequency. Think about what this means for a possible countermeasure against hypersonic missiles, which will remain pretty much a panic subject. They must have strong radomes to fly that fast, and they got to be pointy. Now, interestingly, it appears that crosspole can cause hard kill, physical destruction of the missile caused by the missile hitting the sea surface. This might be possible for at least some missiles which are guided in azimuth and elevation, but it might also be possible for sea-skimming missiles which use an altimeter. Now, whether or not it is possible for sea skimmers depends on whether the missile has cruciform wings, how intelligent the autopilot is, and maybe what the stability margins are in the missile's flight dynamic control system. In any case, to make this happen, the crosspole waveform, I say, must be coupled to the seeker by an intelligent jog detector built into the jammer. Now, this is doable in the real world, so say I, using a cognitive controller, and I designed one called Invicta. Frankly, I didn't think anyone would believe me unless it was demonstrated, which it was 7 years ago in hardware-in-the-loop tests against 4 seekers to spectacular effect. In any case, the possibility of hard kill by crosspole jamming is interesting because hard kill is normally associated with shooting down a missile with consumables like bullets or anti-missile missiles, which you will eventually run out of. But a ship will never run out of electricity to run a jammer. Now, I think the main problem with crosspole jamming is that it's not adequately understood. There have been observations of, in quotation marks, interesting effects, but what's missing until now is the underlying instruction for how to use it for ship defense against missile attack. As a result, the proverbial baby has been thrown out with the bathwater. And actually, there is a very elegant, predictively useful explanation of crosspole jamming that hints at a possibly universal countermeasure, something working against all missiles, past, current, and future. A cognitive one that links crosspole with monopulse antenna design through electromagnetic principles. It's a single theory that applies to other angle deception countermeasures, including off-board decoys and various versions of cross-eye jamming like sector cross-eye, polarization cross-eye, and the 3 versions of double cross. By the way, I'm not advocating that these need to be studied. That's not what's going on here. My point is only that they can be understood by the same theory. Now, that said, in my experience, knowledge about these other countermeasures is practically helpful in programming and using a crosspole jammer. A description of the theory is out of the scope for this video. It's better first expressed as a technical paper, which I will get around to writing at some point, and then as a summarizing video. So here are the broad strokes concluding points of this video. Number 1, crosspole jamming appears to be poorly understood in the electronic warfare community and has consequently remained largely unused or misused. In some quarters, it's been discredited altogether, I believe, as a result of just poor understanding. Point 2. Without exception, the antenna of every seeker I have ever tested with can be moved by cross-pole jamming. And yes, it's fully understood that moving the antenna doesn't cause the missile to miss the target, but that's the direction we're going. Point 3. I haven't elaborated here, but there are previously unrecognized patterns in seeker angle response to cross-pole jamming that I've called angle response modes. I've seen these for years before I recognized them. The angle response modes are present in every single seeker I'm aware of, have ever tested with, no matter what the antenna type. They appear to be a universal effect that is baked into the monopulse design, or the design of any tracking radar, basically, antenna. Point 4, there is an underlying theory which perfectly explains the effect of cross-pole jamming and why the angle response modes are expected to be universal. This underlying theory is out of scope for this video. Point 5, although it's not elaborated here, the cross-pole theory and angle response modes can be exploited by I'll call it a cognitive cross-pole jammer, to possibly place the missile flight path under the jammer's control and certainly cause a missile to miss and possibly cause physical destruction of a missile, at least some missiles. Point 6, for anyone who's interested, cross-pole is a possible countermeasure against hypersonic radar homing missiles. I hope it's obvious from the cursory look presented here that there is considerably more to this story. That said, this concludes an introductory explanation of cross-polarization jamming.